All right, number 2. An 82 kilogram man drops from a diving board 3 meters above water. After hitting the water, he comes to rest in 0.55 seconds. We need to find the net force that stops him. So, when it comes to getting that net force, we need to first find the speed that he has right before hitting the water, because it is the water that is going to be applying force to him to get him to stop, actually come to a rest. So at that point of contact on the water, we will have an initial velocity, right? That'll give us the initial velocity. So since he falls from rest, we can use a version of a kinematic, right, where we can rearrange a kinematic. We can go final velocity is equal to, again, we have to use a square root here, so I'm going to include this either plus or minus. Hint, there actually is a exact sign that I should use, but I'll explain that in a second. 2a delta y. Now I can use this version of the kinematic because there is no initial velocity, because he just jumped off of a diving board, right? So initial velocity 0, I can get rid of the initial velocity. I'm going to use delta y, obviously, because he's falling, so the change of direction is happening, the change in position is happening in the vertical direction. Now, if I plug in what I have, I'm going to go plus or minus 2 negative 9.81 meters per second squared. And my change in position is down, so negative, down 3 meters. That's going to give me a plus or minus 7.7 meters per second. So plus or minus, which one is it? That's important, right? Yes, it is. Remember, this man is diving off of a diving board. Which direction is he falling? Down. And so the direction of his velocity is going to be negative. Well done, logic. Okay. Now that we have a velocity, right? We have an initial velocity, and then we know what the final velocity is. It's 0. So let's find the impulse that is needed to successfully stop him. Because remember, he's in free fall, right? He's diving off a diving board. He's falling. How much impulse, how much do we need to apply to him, meaning the water? How much does the water have to apply to him to get him to actually stop? So delta B is equal to mass times delta V. Again, similar to number 1. What I have, 82 kilograms multiplied by negative 7.7 meters per second. Remember, that's my change in velocity. And that's going to come out to be, what do you say, calculator? So I have a change in momentum or impulse. Remember, this is the same thing. Change in momentum is impulse. Impulse is change in momentum. They're the same thing. All right, so I can use those terms interchangeably. Now I know that my impulse, change in momentum, is equal to force multiplied by time. Here, I'm trying to solve for net force. So I'll divide both sides by delta T. That'll cancel out. So I get force is equal to my change in momentum, which I just calculated, by my change in time, which is given to me by the actual problem. So a plug and chug. Whoa. You guys ever get that where your hand just writes something that's absolutely not even close to what you need to be writing? Yeah, it's annoying. What was my time? 0.55 seconds. Again, seconds will cancel with seconds, leaving behind kilograms multiplied by meters, which is the same thing as a Newton. So a Newton. Now, I need to report 2 sig figs, right? 2 sig figs in my answer. So I'm going to round this to 1.1 times 10 to the third newtons. Now, force is a vector quantity, so I need to indicate what direction this is happening. So I'm going to have to write something very complicated, the word upward. Yes, the force is being applied upward because the man's jumping off of a diving board. You guys know how pools work. You are falling down into the pool. So in order to stop your movement down, there needs to be that equal and opposite applied in the, in this case, the upward direction.